Mrs.W.Felcia Rajam, Assistant Professor, Department of Mathematics, Faculty of Science and Humanities, Bharat Institute of Higher Education and Research, is going to deliver the lecture from Transforms and Partial Differential Equation under the topic Fourier Series. Fourier Series. What is the meaning of Fourier Series? Fourier series is to represent any periodic signal x of t. It was developed by Fourier. It is an expression called as Fourier series. This is in terms of an infinite sum of sines and cosines or exponentials. Fourier series used orthogonality condition. Now we will see about the person who derived Fourier series. It was derived by Jean-Baptiste Joseph Fourier, a French mathematician and a physicist. He initialized Fourier series, Fourier transforms, and their applications to problems of heat transfer and vibrations. What are the applications of Fourier series? Fourier series are widely applied for seeking the solution to various ordinary differential equations and partial differential equations. It is applied in electrical circuit and digital multimedia visualization signal process of communication system. It is used in quantum mechanics and image processing. It has many applications in electrical engineering, vibration analysis, acoustics, optics, signal processing, image processing, quantum mechanics, and econometrics. Now, we will see the definition and the representation of Fourier series. Fourier series representation of continuous time periodic signals. A signal is said to be periodic if it satisfies the condition f of x equal to f of x plus capital T, where T is equal to fundamental time period. The least value of T greater than 0 is called the period of f of x. Periodic signals. There are two basic periodic signals. They are sinusoidal and complex exponential. We will see the example of a periodic function. So let us take a function f of x which is equal to sin x. So this is equal to sin of x plus 2y, which is equal to sin of x plus 4y, x plus 4 pi, etc. We are taking a function that is sin x. So we are writing as f of x is equal to sin x. So which is equal to sin of x plus 2 pi. Next, sin of x plus 4 pi, etc. So here the function has periods 2 pi, 4 pi, 6 pi, etc. And among these, the least value 2 pi is called the period of sin x. Note, sine, cos and its reciprocal has periodic function with period 2 pi. Tan and cot has periodic function with period pi. Sin nx and cos nx has periodic function with period 2 pi by n. Now we will see the definition of Fourier series. If f of x is a periodic function and satisfies the Dirichlet's condition, then it can be represented by an infinite series called Fourier series. Now, what is the expansion of Fourier series? So, how it is expanded? Fourier series is expanded as f of x is equal to a0 by 2 plus summation n equal to 1 to infinity an cos nx plus bn sin nx. So, this is the expansion of Fourier series. A0, An, Bn are called as Euler's coefficients. Fourier series for the function f of x in the interval c to c plus 2 pi is given by f of x is equal to the expansion, that is a0 by 2 plus summation n equal to 1 to infinity an cos nx plus summation n equal to 1 to infinity bn sin nx, where a0 is equal to 1 by pi integral over c to c plus 2 pi f of x dx. An is equal to 1 by pi integral over c to c plus 2 pi f of x cos nx dx. Bn is equal to 1 by pi integral over c to c plus 2 pi f of x sin nx dx. Now we will see what is the meaning of Dirichlet condition. Any function f of x can be expressed as Fourier series provided f of x is single valued and finite number. Second one, f of x is periodic with period 2 pi. Third one, f of x and f dash of x are piecewise continuous in the interval minus pi comma pi. What is the meaning of piecewise continuous function? A function f of x is said to be piecewise continuous in an interval if the interval can be divided into a finite number of subintervals in each of which f of x is continuous. Next topic, we will see what is the meaning of even function and odd function. So a function is said to be an even function if it satisfies the condition f of minus x equal to f of x. So let us take an example as x square. So if you substitute the value of x square, you get it as minus x the whole square. So minus x the whole square is same as x square, which is equal to x square. Therefore, our condition is satisfied. That is f of minus x equal to f of x. So we call x square to be an even function. Few more examples for even functions are cos square x, sin x, etc. Next, a function is said to be an odd function if f of minus x equal to minus f of x. So we will take an example as x cube. If we substitute in place of x as x cube, it is minus x the whole cube, which is equals to minus of x cube. So f of minus x equal to minus f of x. This condition is satisfied. So we take x cube to be an odd function. One more example of odd function is sin x. Note, the product of two even functions or two odd functions is an even function. Product of even function and an odd function is an odd function. If the function is an odd function, then it can be written as integral over minus pi to plus pi f of x dx equal to 0. If the function is an even function, integral over minus pi to pi f of x dx is equal to 2 into integral over 0 to pi f of x dx. Then f of x is an even function. The Euler's coefficients a0, an and bn are given by a0 is equal to 1 by pi is equal into integral minus pi to pi f of x dx. This can be written as 2 by pi integral over 0 to pi f of x dx. Similarly, an is equal to 1 by pi integral over minus pi to pi f of x cos nx dx. This can be written as integral over 0 to pi by multiplying a 2 outside. So 2 by pi integral over 0 to pi f of x cos nx dx. Next is bn. Bn is equal to 1 by pi integral over minus pi to pi f of x sin nx dx, which is equal to 0. When f of x is an odd function, then its Fourier expansion contains only sign terms where f of x is equal to summation n equal to 1 to infinity bn sin nx. Bn is equal to 2 by pi integral over 0 to pi f of x sin nx dx. Since a naught an both are equal to 0. Next is change of interval. In many engineering problems, it is required to expand a function in a Fourier series over an interval of length 2l instead of 2 pi. The transformation from the function of period p equal to 2 pi to those of period p equal to 2l is quite simple. This can be achieved by transformation of the variable. Consider a periodic function f of x defined in the interval c less than or equal to x less than or equal to c plus 2l. To change the interval into length 2 pi, we are substituting z equal to pi x by l. So when x equal to c, z equal to pi c by l, which is equal to d. When x equal to c plus 2l, we get z equal to pi into c plus 2l divided by l. So if you separate the denominators, you get it as pi c by l plus 2 pi l by l. If l and l gets cancelled, the remaining is 2 pi. So already we know that pi c by l is equal to d. So we get it as d plus 2 pi. Thus, the function f of x of period 2l in c to c plus 2l is transformed to the function f of lz by pi, which is equal to f of z of the period 2 pi in d to d plus 2 pi, and f of z can be expressed as the Fourier series. Proof. F of z is equal to the expansion a naught by 2 plus summation n equal to 1 to infinity an cos nz plus bn sin nz, where a naught is equal to 1 by pi integral over d to d plus 2 pi f of z dz. An is equal to 1 by pi integral over d to d plus 2 pi f of z cos nz into dz, where n equal to 1, 2, 3. Similarly, Bn is equal to 1 by pi integral over d to d plus 2 pi f of z into sin nz dz, where n equal to 1, 2, 3, etc. Now making the inverse substitution, that is z equal to pi x by l, dz is equal to pi by l into dx. When z equal to d and x equal to c, and when z equal to d plus 2 pi and x equal to c plus 2l, the expression 1 is changed as f of z is equal to f of pi x by l is equal to a naught by 2 plus summation n equal to 1 to infinity an cos n pi x by l plus bn sin n pi x by l. Thus the Fourier series for f of x in the interval c to c plus 2l is given by f of x is equal to a naught by 2 plus summation n equal to 1 to infinity an cos n pi x by l plus bn sin n pi x by l, where a naught is equal to 1 by L integral over d to d plus 2L f of x dz. An is equal to 1 by L integral over d to d plus 2L f of x cos n pi x by L into dx, where n equal to 1, 2, 3, etc. B is equal to 1 by L integral over d to d plus 2L f of x sin n pi x by L into dx, where n is equal to 1, 2, 3, etc. Now we will learn an example. Obtain the Fourier series for the function f of x is equal to pi x in the interval 0 to 1 and pi of 2 minus x in the interval 1 to 2. The period given to you is P equal to 2L equal to 2. Solution. Let f of x is equal to a naught by 2 plus summation n equal to 1 to infinity an cos n pi x by L plus bn sin n pi x by L, where a naught is equal to 1 by L integral over 0 to L f of x dx. Now we have to find out our length, that is L. So 2L is equal to 2. So from this L is equal to 1. So now substituting the value of L as 1, we get it as 1 by 1 integral over 0 to 2 f of x dx. So now we are going to substitute the value for f of x. So f of x given to us is, first one, in the range 0 to 1, the value is pi. So integral over 0 to 1, pi x into dx, plus the second function is pi into 2 minus x in the length 1 to 2 into dx. So here pi is a constant. In the first integration, we are taking out pi outside. Remaining integrating x dx, you get it as x square by 2, applying the limit as 0 to 1, plus pi into 2 in 2 is a constant. Integral of dx is x minus x dx is x square by 2. The limit given to us is 1 to 2. Applying the upper limit and lower limit, and for solving, we get the final answer for a naught to be equal to pi. Next is an. So an, the formula is 1 by L integral over 0 to 2L f of x cos n pi x by L into dx, which is equal to 1 by 1 integral over 0 to 2 f of x cos n pi x into dx. Now again we are substituting the given functions as pi and pi into 2 minus x. When the value of pi is in the limit 0 to 1, we are substituting it here. Here it is x into cos n pi x into dx plus pi into integral 1 to 2 minus x cos n pi x into dx. Now, in the first kind of interval integration, we can see that you have two functions, x and cos n pi x. So, both cannot be integrated together. So, we are applying Bernoulli's method of integration. So, Bernoulli's formula of integration is u v1 minus u dash v2 plus u double dash v3. So u is x, v1 is nothing but integration of cos n pi x, which is sin n pi x divided by n pi. U v1 is over. Next, u dash minus of u dash, u is x, u dash is 1. So it is 1 into integration of v1 is v2. So it is sin n pi x integration is minus cos n pi x. And already there is a n pi. So one more n pi multiplied, we get it as divided by n square pi square. The next term will become 0 because u double dash is 0. So this is the first part of the integration. The second part of the integration is 2 minus x, which is u. Integration of cos n pi x is sin n pi x divided by n pi. U v1 minus u dash. Integration of 2 minus x is minus 1 into v2, which is cos n pi x divided by n square pi square. Now, after this, we are just substituting the limits. Finally, you take the value of n pi sin n pi to be 0, sin 2 n pi to be 0, cos 2 n pi to be 1. Substituting all these values and solving the above, we get the final answer as 2 divided by n square pi into minus 1 power n minus 1. Now, since because you have minus 1 power n and divided by n square, this answer for an has two values. When you substitute a value of n as an even number, we get the answer to be 0. If n is an odd number, we get the answer to be minus 4 divided by n square pi. So, an altogether has two values. One is n when it is even, other one n when it is odd. Next one is bn. Bn is equal to, according to the formula, 1 by L integral over 0 to 2L f of x sine n pi x by L into dx. So substituting the value of L as 1, we get it as integral over 0 to 2 f of x sine n pi x into dx. Now again we are substituting the function as pi x and pi into 2 minus x. So first integration, pi is a constant which is removed outside, integral over 0 to 1 x into sine n pi x dx plus pi into integral 1 to 2 2 minus x sine n pi x into dx. Now we are integrating the first term. We get it as, by Bernoulli's method, we get it as uv1. So it is x into v1. Integration of sine theta is minus cos theta. So minus cos n pi x divided by n pi. uv1 minus u dash. Integration of x is 1. So it is 1. v2. v2 is integration of v1. So cos n pi integration is sine n pi divided by n pi. Already there is an n pi. So it is n square pi square. So first integration is over. Plus second integration pi into 2 minus x sine n pi x into dx. So 2 minus x, that is u v1. v1 is sine n pi x. Integration of sine theta is minus cos theta. So it is minus cos n pi x divided by n pi minus of 2 minus x. Again you differentiate, it is minus 1. Integration of v1 is v2. So we get it as minus of sine n pi x divided by n square pi square within the limit 1 to 2. Now applying the limits, finally our result is equal to 0. Substituting the values of a0, an and bn, we get the final expansion as f of x is equal to pi by 2 minus 4 by pi into cos pi x divided by 1 square plus cos 3 pi by x divided by 3 square plus cos 5 pi by x divided by pi square plus etc. Next example, find the Fourier series with period 3 to represent f of x equal to 2x minus x square in the range 0, 3. So here also L is calculated by using the formula 2L is equal to 3. From this L is equal to 3 by 2. For this period 2L equal to 3, we have the expansion f of x equal to a0 by 2 plus summation n equal to 1 to infinity an cos 2n pi x by 3 plus bn sin 2n pi x by 3. Here a0 is equal to 1 by L integral over 0 to 2L f of x dx. So we are substituting L value as 3 by 2, which is already found. So if we do that, 2 into 3 by 2, 2 and 2 will get cancelled. So finally 2L value is equal to 3 alone. So in place of L we are substituting as 3 by 2. Then you get it as 1 divided by 3 by 2. Its reciprocal is 2 by 3. So which is equal to 2 by 3 integral over 0 to 3 2x minus x square into dx. The given function 2x minus x square into dx. Now 2 by 3 is a constant outside. 2 into x integration is x square by 2 minus x square integration is x cube by 3 within the limit 0 to 3. Next one is an. an is equal to 1 by L integral over 0 to L f of x cos n pi x by L into dx, which is equal to 2 by 3 integral over 0 to 3 2x minus x square cos 2n pi x by 3 into dx. So 2 by 3 is outside. Integrating by using u v1, you get it as 2x minus x square into cos integration is sine 2n pi x by 3 divided by n pi x by 3. So this is 3, taking the reciprocal, you get it as 3 divided by 2n pi into sine 2n pi x by 3 minus 2 minus 2x, that is v1, 2 minus 2x is u dash, next one is v2 plus u double dash v3. After applying the limit from 0 to 3, we get the answer as 3 by n pi. Substituting all the values, we get the final Fourier series as f of x is equal to minus 9 by pi square summation n equal to 1 to infinity 1 by n square cos 2n pi x by 3 plus 3 by pi summation n equal to 1 to infinity 1 by n sin 2n pi x by 3. Next example, find the corresponding Fourier series f of x is equal to 8 when it is in the range 0 to 2, minus 8 when it is in the range 2 to 4. The limit range given to us, that is period, is 2L, which is equal to 4. So we are calculating L here. So 2L is equal to 4. So L is equal to 2. So f of x is equal to a0 by 2 plus summation n equal to 1 to infinity an cos n pi x by 2 plus bn sin n pi x by 2. a0 is equal to, substituting the values of the function 8 and minus 8 and integrating, we get the value of a0 to be equal to 0. Similarly, an is equal to 1 by L according to the formula 0 to 2L f of x cos n pi x by L into dx. So value of L we have found to be 2, 1 by 2, integral over 0 to 2 into 2, which is 4, f of x cos n pi x by 2 into dx. L is 2. Now substituting the value of the function 8 and minus 8 and taking out it as a constant and integrating, we get the value of an to be equal to 0. Finally, we are going to find out bn. Bn is equal to 1 by L according to the formula 0 to 2L f of x sin n pi x by L into dx. Substituting f of x and integrating, we get the final answer to be equal to 16 by n pi into 1 minus minus 1 to the power of n. When you have n, we have two values. When n is odd, we get 32 by n pi. When n is even, we get it as 0. Substituting the values of a0, an and bn, the final series is f of x equal to 32 by pi into 1 by 1 sin pi x by 2 plus 1 by 3 sin 3 pi x by 2 plus 1 by 5 sin 5 pi x by 2 plus etc. Thank you.